might be.
Отлично.
Hello, guys.
Спасибо, что пришли.
Apparently, you can hear me well. Thank you so much for coming, particularly on a Sunday at 11 a.m.
Я это правда ценю.
Yeah, I do appreciate it.
Сегодня хотелось бы поговорить о защите,
The
проактивной
plan today
защите
is that we
операционной
discuss
системы Linux.
proactive
И этот доклад, он
measures
как бы
for Linux
является продолжением моих
systems.
предыдущих двух докладов.
It's effectively a continuation of my two previous
На них я
reports,
рассматривал существующие способы защиты
where I talked about
операционной системы Linux
existing
в, так
methods
скажем, в реальном
for a
времени.
Linux operating
Я
system
являюсь
in real
разработчиком
time.
EDR,
Now, effectively, I am a developer
про
of
это
EDR
вроде как
solutions,
знать. Что
and I'm
рассматривалось?
sort of
Я
expected to know something about
рассматривал
it.
защиту на уровне ядра, написанием ядерного
So what I
модуля.
was
Такой
looking
самый
at
простой и
was
очевидный вариант,
the
который нам
kernel
дает большее
protection
количество привилегий.
by, say, developing a kernel module.
Рассматривалась уже защита
That was
искусственного
my first presentation. The second one looked at the user space
механизмов безопасности по типу
and numerous security measures there, such as NTFI and F.A.C.C.T and so on and so forth.
защиты, это можно назвать только
However,
натяжкой, но да ладно.
you can call it security, and that will be a bit of a
На сегодняшний
stretch.
день, наверное, вот актуальное, используемое
And probably the thing that's most topical today is eBPF.
не лишены недостатков.
Unfortunately,
В частности,
all these
если мы
options
пишем
have
ядерный
got
модуль, то
their
единственная
drawbacks.
ошибка
For
в
example, if
нашем
we do the
коде,
kernel
лучшем
module,
уронит ядро, в худшем откроет
like
еще одну дырку, через
a
которую
single
пройдет
error in the
и
code
прочее. Что как бы
may
вроде как
down the
противоречит,
kernel or create exploits and vulnerabilities. I'm sorry, vulnerabilities to be exploited. Now, if we're only protecting the user space, like I said, is not really security. It's more like monitoring, and it's not entirely consistent because information sources will differ quite a lot. There is little consistency between them. So it's not really high-quality monitoring either. Finally, eBPF, something that appears to be the most progressive and advanced technology today, but it's got so many delicate issues of its own that developing eBPF is not exactly undesirable, but certainly
если поразмыслить, а что мы реально хотим видеть от какой-то
So I asked myself what we would like to get.
систему такую защиты информации.
Like, how can we really provide proper security for Linux OS?
Мы всегда хотим поставлять, как разработчики,
like as developers,
наше ПО в виде просто
we usually want to provide our software as a binary, right? Not, as VM codes, as you would do for a BPF. And naturally, want to write in modern programming languages, not just in C.
Тоже камень в сторону eBPF с их Core.
And compatibility is certainly an issue with the eBPF. So BPF is not ideal. There are expert issues as well. You can bypass those issues, but that requires quite a lot of extra efforts. Kernel level control can be done, but if one event consistency, it means that we are getting all the information in the same format from a single source, and it should be sufficient, right?
И обеспечение механизмов доверия к ВПО — это опечатка. Мы не доверяем вирусам и вредоносному программному обеспечению.
And naturally, we need to provide some, trust methods to protect against malware.
Нужно написать какой-нибудь свой фреймворк.
So I realized I had to develop my own framework for the Linux core, something that would be similar to Mac policy and would meet all the kind of criteria I've just mentioned. I came up with this idea last year. I invited people to collaborate with me, and there was interest in that, but it was sort of lukewarm. Like, people said they were interested, but nobody really helped me. So I worked alone, and I'm happy to present to you a prototype of Endpoint security framework as it stands today. So, very briefly, let's look at what it can do, how it works, what the advantages are, and what still remains to be done.
QR-коды с ссылками на исходные коды, так как я не могу...
I'm sorry, in the website, you can find through the QR codes, you can obviously find, well, the code base itself. I'm not going to show you thousands of lines of code here for obvious reasons. And I should also mention that it's a sort of an experimental presentation. It is still stuffed with code. I hope some people here will appreciate that.
Вот как представляется вся система взаимодействия ESF и агентов.
This is the whole system for ESF, and we have agents here, like security agents, or a piece of software which is using endpoint security framework. So we have some character device on Linux, which is using TTL to do all the communications.
Взаимодействие у нас осуществляется через IOCTL. В дальнейшем,
I'm sorry, IOCTL is being used. So then, if you create file descriptors for the agents to do, proper configuration of individual agents, there are also two types of channels. They are effectively event providers. So they have IOCTL as their interface, but there is also the regular interface for read, write, pull, and other operations. So that's what it looks like. IOCTL today is pretty simplistic. These are basic structures that show your API version, and the basic work is effectively, a call on device or an open ESF file descriptor to do some channel work. So look at the first structure here. I don't think you can actually see it online, but so you can see the first struct here to register the agent. Now structures 2 and 3, they open channels for listening to the kernel events. And the last one helps us control what's happening in the system, based on the decisions made by the agent. Once an agent has been set up and initialized, its file descriptors will look like this. So, for example, descriptor number 4 is descriptor of ESF agent established by the subsystem, followed by the authentication channel, which enables us to control what's happening in the system and obtain events such as read, write, and so on. And in the listen channel, we can obviously listen to events without any losses in terms of system performance. Now, this is how you deal with channels. So, like I said, we have some base structures such as subscriptions. And as we set a filter for the channel, we should be able to establish rules. Like, now we don't want to learn about these events, or it's just these events that we want to hear about, but we are going to cover it in more detail a bit later. And everything has become darker because we are going down into the kernel. Now, let's see what inside the kernel the agent looks like. Now, the agent itself is a structure like this. It probably makes a little sense for us to discuss all the lines here in the fields, but Ctrl+F-D is the interesting one because it's a file descriptor that will be available for agents post-registration. Next, we have flags, which are effectively your regular masks. And by the way, how many people here know C and develop in C? Wow. I'm not even going to ask you the awkward question of how many of you have explored the kernel. Okay, and we have two entities for channels, auth channel and listen channel. And finally, we have task, which is effectively an agent process. If so many people have done C development, I will probably need to provide some extra instructions. So task struct is a structure inside Linux kernel. That's used for most flows. So after, so what happens next is that first signatures are checked. That is the digital signature for the binary file. Next, resources get initialized, and then, registration in subsystem happens. In fact, it's a pretty simple process. As structures get allocated, some fields are getting filled out in the registration is that you get registered in a global context.
В данном случае регистрация пока что представляет из себя
Well,
просто
at the moment, registration here
список. Вот.
is more
Куда
like,
интереснее посмотреть
you
на
know,
то, как
making an
происходит,
entry in
подпись,
a list.
и
What's
проверка
much more interesting is to see how signature
происходит она
verification
следующим
is
образом.
done.
Я, когда все это писал, не стал ничего
So
нового
as I was doing that,
придумывать.
you know, rather than inventing
Придумали,
anything new,
уже
because, you know, everything
существует
has been invented
механизм
already. Now, there is a
проверки
mechanism
ядерных
in
модулей,
the Linux
который я
kernel
просто
for
взял и скопировал.
checking
Потому что это
the
больше
signatures,
всего
and I simply copied it because it's the easiest thing to do.
в текущем репозитории ядра Linux
So that's the verification for the kernel module signature.
файлик,
Now, in this script folder,
который умеет
there is a
подписывать
C
бинарные
program
файлы, и
which knows
подпись там в
how
каком-то
to
формате. Это выглядит как
kind of
просто
verify or
мы
subscribe
забахали
binary
файла
files.
эльфа, так как
So we
это
simply
было
append
сначала. Ой,
the signature to the end of the
и
file,
забахаем маленькую структурку
and
метаинформации.
then we append a bit of meta information about the
Это
signature
позволяет
itself.
просто брать
This
функции, которые существуют, и
helps
писать
us
нечто
grab
своего.
those kernel functions rather than, you know, develop something on our
Уже
own,
готовый механизм проверки подписей.
you know, reuse the
Самое
already
главное,
existing
это помогает,
signature verification method,
вот использование именно этого
and it
механизма
also
помогает
helps
нам
us
осуществить две фичи. Первое, ядро во
perform
время
two
сборки
things.
генерирует
One is
для
that
себя
the kernel will generate
сертификаты, ключи, которые
certificates and
впоследствии можно
keys,
использовать для
which can
подписывания
later be
ядерных
used
всего того,
to
что
subscribe to kernel modules, and pretty much anything else you want to
это то,
subscribe,
что по умолчанию, вот
or
если
sign, rather.
посмотреть на вот этот вот флажок secondary key ring, говорит нам о
Now,
том,
if you look here, the
что
secondary key
ядро,
ring flag, you will see
во время
that
проверки подписи
the
будет
kernel,
использовать два
as
key-ринга
the
на самом деле.
signature
Secondary key ring
is
это
being verified, is going to use two key rings. One
позволяет
is
нам,
what's
как
got
вендорам,
imported,
говорить
which enables us as vendors
если вы нам доверяете, просто зашейте наши ключи в ядро.
to say, well, if you trust us, dear users, you can just build our keys into the kernel.
Ядро, имея наши ключи, сможет
And then the kernel, as it has our keys, should be able to verify what the agents are doing. And during the kernel compilation stage, we should also be able to invoke
это верификация на
what's relevant here, which is vendor-side verification, the way Apple does it. In fact, during my presentation today, I am going to refer a number of times to Apple solutions. Now, what's good about it is that the vendor should be able to sort of validate and guarantee that the software they provide is bona fide, valid, it has been checked by us or the vendor, it is properly signed, and it can be used in the ESF file. And all this is needed in order to limit access to API because, well, you can have quite a field day with the API. We've talked about the agent and the signatures. I've mentioned channels already, now let's talk more about them. Globally speaking, channels are a kind of an abstraction on top of the event queue. I think if you're a developer, you know exactly what I'm talking about. So, a queue events, an event queue, you see where it's going. So, let's look at the structure here. Let's disregard the service fields except for two. So FD obviously is the channel file descriptor, since the channel is available in user space. There should be a descriptor. Agent subscriptions mask is the mask of subscriptions, something that we are going to discuss later. Next, we have events queue, which underlies the channel. Next, we have channel CTL, which is a structure similar to virtual elements in C++.
извне определять поведение канала. То есть это структура
So effectively, it's a system with callbacks.
Дальше у нас идет channel owner.
Next, we have channel owner, which is simply information on the process which currently owns the channel. And finally, filters. We are going to discuss filters a lot a bit later. First, about the CTL, like I promised. Now, currently, channel behavior is driven by several different factors. First, we have callbacks that can help us learn what the situation is without making any changes. Well, some can be used to introduce changes. Now, there is a callback called won't wake up. So if the agent is in a calling state, it sort of tells us when the agent's got to be woken up and inform him that, there are new events for him to process. Now, event filtered means that some event got filtered out. Event past filters is a callback that says that this particular event went through filters and didn't meet a single them. And a release is effectively a destructor that you invoke to close the channel. Next one is won't wake up. One of the key differences between channels is that how they wake agents up. Now, with the listen channel, we don't really need to wake agents up every time because that would mean performance overheads. The kernel would have to give more priority to the agents. And since you don't have a single agent running on, like you have more than one agent running, that's a bit of an overhead. Now imagine that an agent gets an event and immediately gets another one while it's still busy working on the first one. So listen channel will only wake up once in 100 events. And naturally, you can set up it from user space. So it doesn't have to be 100, but the variable is there. So if it's woken up with every nth event in the queue, the big question is, what if you have very few events? Like if you only have 98 events in the queue and the threshold is 100, and then, event 99 arises and it's so important, you really want to see it, but you still have to wait. So it's suboptimal. That's why in agent registration, there will be a kernel flow, which every 100 milliseconds will be sort of bashing the events. And I consider it to be the best solution. That's what I've implemented. However, for auth channels, the situation is different. Now, if you look at these lines of code, you will realize that we are waking the channel up with every event, because events that require, say, authorization, they should be important, right? And if the agent is not working well, you can seriously slow the system down. That's why we want to wake the agent up for every event in the auth channel. And, I've done some simple perf tests, and they show that this was the best solution I could have come up with. Now, I promised to talk a bit about filters. Now, the filtration system is the one that attracted most of my attention. First, it had to be convenient if it's C, because, for the kernel, we will be using C, and it's not an easy task. Why is a filtration system so important, and why would I devote so much time to it? In modern systems, the desktops or servers, so many useless events are happening at the detect stage, for example. But what do I mean when I say they're useless? Now, raise your hand if you're doing proactive security, CMs, EDRs, or maybe detection, or maybe you're into signatures. Do we really need to know that Zavix server is pinging the agents to see if they're alive or not? I can give you so many examples that show how we are shooting ourselves in the foot in terms of performance. In any case, agents will be using filtration on their side in the user space. However, there can be so many events, like 2,000, 3,000, or 10,000 events per second. In high-load systems, we can be talking about, say, 2 billion events per week. All these events need to be filtered. It will be lousy if we tell our agents, now filter all these events in your own CPU time. And even if it gives itself like 100% priority, they won't work. So the best solution here is to give the user space agent some simple filters and then use the kernel so that filtration happens during the CPU time for all the processes that give rise to a given event. This way you spread filtration across the system. It will be pretty dumb and stupid, but it will be fast. Now, this is the structure of filters. I guess this is the easiest structure, or at least this is the only structure that can be copied from user space in full, as it contains no dynamic fields without a predetermined size. So type is obviously filter type. Currently, there are two. One is allow, the other one is a drop. They are often called positive and negative filters. Next one is match mod. And match, which we are going to discuss in the next slide. Next, we have 3 fields, which are considered the payload of the filters, as they are going to contain fields that you will find in real events, and they will be compared in a particular way. Now, match mode and match mask. Match mode is and or. This is the kind of logic that will tell us that we are planning to match the fields shown in the filter using a particular logic, such as the path to process is such and it has such and such PID. And then, if this is the case, it will be ignored. And if it's, and obviously the options here are and or. If it's a match mask filter, then it's a purely service field. So it's a filter mask that tells us that such and such fields are indicated in the filter. Since it's done in C, we cannot dynamically add fields. We should be able to tell the framework one way or another that we want these fields to be checked. Please note that there is no full proofing here built into it, so gotta be careful. Now, letter M here, just remember it, okay? Because there will be a Boolean value later on my presentation with letter M. Maybe even a question related to it. So, like I said, we take the match field here. If it's there, we'll take, the target PAF, or target path, I'm sorry. So that's the path shown here. Interestingly, we're going to check it in global, because it's a fast algorithm. And, having it in filters really helps. Statistically speaking, about 90% events, roughly, note what I'm saying, because this statistics is something I have in my mind, like so many events can really be filtered out if you use the right glob, which is certainly an advantage of such filtration. Another advantage is that, this is C, so it works very fast. Comparing, yet another line in the path doesn't cost you anything. No, we're not trying to, run around Dentry or any other structures as exec would do when it's looking for the path to an executable file. So overheads are pretty much zero. Now, what's bad about filters is that you cannot set, logical expression between filters you can only do it at the level of fields. It can be fixed, but I have not really seen much value in doing it myself. Because if you need complex filters, you can do it in user space. And to support a new field, there is no automation at the moment. It's all manual work, which is obviously a disadvantage of the filter interface. So besides this relatively complex filters, there is a mechanism which is related, in my opinion, to filtration mechanisms, though not filters themselves. Now, you might remember we mentioned something when we talked about subscription masks. Now, give me some attention here. So, what we're looking at here is an array of int64s. Since there could be numerous events, more than 64, and we want to tell the kernel, I am an agent and I want to get such and such event. We are not going to keep 64 Boolean values for that, but you are going to grab an int. But if 64 is little for you, you can do what I did. So I put them into categories and I created this array. This way we can expand the bit mask to cover as many events as we want, as long as these events are properly categorized. And at every hook entry, we will be checking if such an event needs to be created or not, because if nobody wants to listen to it, we can simply skip the whole hook, which is efficient, isn't it? Now, if you look at the initial code here, the ones used for event announcing, you're going to see lots and lots of ugly macroses. And they look like this. And they tell us that we have this base of categories, which gives us the steps and whatever. And since everything is announced in enum and event type is, just a figure there, so we can say that process events are, say, 100 to 200, event items, so to speak, are 200 to 300, and so on. So event category base is a category base which is equal to 100. And there is also an auxiliary macros that I'll be talking more about in the next slide. We use it in order to grab the number of the category. So see here, for category process, number is 0, for file it's number 1, and so on and so forth. And now you also see here 3 macroses which get used a lot in the framework. For example, MR, type MR event gives us the bit number, and in the category mask, and type mask gives us the bit mask for a particular event inside the category. I understand it should sound a bit crazy to you, but all these checks are required to make sure that this is what we have in the end. So when a new event arrives, we will know its type from the outset. We should be able to get a category for it simply by dividing its number by 100, disregarding the leftover. Well, because in C nobody cares about it, A, and B, in the Linux kernel, floating instructions simply do not apply. So we'll just get the value, and that's it. So we get the bit mask. Or rather, we take the bit mask, which is the category number, then we offset it to the left, and we take the category from that array. As I'm showing here, so you check the mask, then you apply the mask, and if the value is 0, this means that nobody wants to get those events. Now, it may seem like convoluted logic. However, it helps us maintain a constant speed without running around lists to do the filtration without doing the extra necessary work. A lot has already been said here, right? We have event channels, we have event filters, and all this stuff was in fact invented to make sure we can obtain events and control for them, and we haven't yet talked about events as such, so let's address this. Now, the only structure that should be of great interest to you, and it's also my favorite, is raw event, which is effectively an event which has not been prepared for the user space. Inside the kernel, there are no as-is events. Instead, the kernel is using event interpretations. And I think it will follow from my further speech why this is the case. So there are two service fields here, read and decision, and we need them in order to perform control over events and wait for them properly, or expect them rather. Like I said, we can spawn events that we can control, so we need these two fields in order to control them. So, raw items. Now, this is the field which represents all dynamic fields inside the structure that will then be sent to the user base. And this particular structure is the one that will be completely copied into user space.
And if we are talking about just a list of potential closely connected items, and here data science, we have the additional field that allows us to calculate the range, the size reserved for the event which will be sent to the user space. A few words about the control. I already mentioned two fields which start with decision and narib. If an event is controllable, then during its creation, during its inception, there is a function called submission. You will see a QR code later. If there is at least one agent who wants to control this current event, then it will be added to a special table, and after it is put in query in sequence, they will be waiting for it to be read and for it to be written. This is how it's added to the table. Here we check the flag for the decision, wait for decision, and here we add this to the special wait table. There is nothing exceptional here. It's more interesting how this waiting is implemented. So now the question, if an event was added to the special table and it will block the thread, the execution thread, and then it was filtered. In this case, we have to give a few comments. The filter logic for different channels is different. When we are talking about authentication channels, both filtration with the allow type, which means, yes, they allow this, the event will not get into user space. It will be automatically allowed by filters. So filters at these authentication channels, even policies, not just filters, that help user space remove from these long-winded solutions. All that is for the sake of performance. And obviously we have type drop instead. Then we have the automatic solution that the event was prohibited. It will be dropped from the wait table and deleted later. It will not get into user space. When we are talking about filters that just listen to it, then we either allow an event. If it's allowed, it will get into user space. If it's dropped, it will not get there. You don't need to make a decision on this. I think this is all I wanted to say about the filters. I think it's reasonable and you can just read the name. It's clear what they mean. So this is the general pipeline. An event starts with pre-filtration and it can be dropped from this. Maybe nobody wants to see this. Then it gets into the authentication channel. Just by the way, there are many agents and there are many authentication channels, and that's why it gets into authentication channel for many agents. First, it goes through negative filtration. In case if there is at least one negative filter that would drop, or to block this event, then we drop it, and we drop the event too. Then it goes through positive filtration with the same logic, but if at least a single, obviously if everyone allows it, then event passes, but if none allow, it will be dropped, then it's passed into queue. If they pass through all these filters, after that, they get into authentication channel. No, they go for the listening channel. They go through the same filters, but without taking decisions. And by doing so, just to understand the whole logic and how it's interacting with itself, and you can see it at the bottom. It's in Boolean logic. I hope you can read it. I hope you can see it. Well, I wouldn't ask you because it's not an examination. The M, which I asked you to remember here, you can see it at the bottom. You can see that it's, we can say that if any filter, if function M returns false, meaning if not a single filter was specified, then the expression PF can be interpreted as there is at least a single filter. It means EA-EL is a function or functions which will tell us if the event will be sent or not, if it will be allowed to drop or not. I think it would be easier just to use Boolean logic here at the bottom. That's why I put it here. And obviously we can go back to this slide during the Q&A session. I'm not exactly sure about the most correct solution for the filter. So I think this is a comfortable solution, but when I had the discussion with my colleagues, or somebody who took part in this project, maybe just as a bystander, some third party, just to provide some ideas for filters, they actually had some reservations regarding the perfection of this idea. So maybe this is discussable. So regarding the authentication channel, waiting for decisions on different channels, this is what it looks like. This is a wait for the read. These are the read structures, and it also includes wait for reply. So after an agent would read at least one event, then the kernel turns the event into the next stage, waiting for 0.5 seconds. Even the worst developers would not be able to destroy the system because they have 2.5 seconds for waiting. And the problem of poor developers are solved partially by signatures, which I mentioned before, the validation of agents at the side of distributive developers. So this wait for decision is basically the whole function that performs what I just was talking about. If at least one agent wants to authenticate this event, and this event can be authenticated, then we are waiting for the response. Then we set masks in the event itself, saying that this event somehow passed the authentication and cannot be controlled anymore. Then we set the mask in if it's allowed or if it's disallowed, and then we send this event to where it should be sent if they, for some reason, did not process it before. And finally, what I wanted to cover in this presentation in the event structure is serialization. So we're talking about like the center agents. There are different items. Now let's take a look at the serialization itself. And the meme, obviously we can use different memes, and here we have very tricky layouts. The list of row items actually refers to normal items which are included in the final structure of the event, which will be copied into the kernel. So why do we need this? We do not want to serialize events that, well, obviously you understand what it means to serialize, to get in some kind of planar way. We do not want them to have in a planar way before they are read by user space. And we do this because an event can be big, with very big volume, and we might not be able to fit it in a single slot. We have to use virtual location to fit the whole event. Well, I didn't do this, but theoretically it's possible. That's why this is here. Raw items has a field item, which refers to the item that gets into the event. It has signifiers to data, which are allocated in the kernel. And one of the pluses of this kind of approach is that we do not need to have allocated memory for different agents. We can create a true item. It will be somewhere in the kernel, it will be pointing at the kernel, and it will know where it will be serialized in. So this data science I mentioned before, when we add elements to the event, it will calculate its size, it will take a look at the size once again, and it will tell us that in the user space buffer, it will land somewhere here. And since we know the space, since we know where they're located in the kernel, and since we know where they should be in user space, then serialization is performed fast and it does not require duplication of data for specific agents. And we also get previously, in two previous slides, we were talking about during bit masks for event states. Since we reuse those events, we do not need to apply additional efforts to synchronize the whole machine with some kind of very tricky algorithms. Just to modify a single structure, basically using modifying a single object will modify everything else because we use the same signifiers. And just for a clear understanding how it's structured, we have raw item is the list, which I mentioned before. It has true items. Here we have event structures, which will be completely copied to the user space. And here we have ESF items and raw items, and they point to the structure. So this is a list inside the structure that points at the structure inside itself. It's actually very useful and very comfortable because at the end the serialization looks like this. We'll just go through the whole list and we'll say, since we have already pre-calculated the size, we already know the location of data, we know that they are valid. And by the way, we already know the offsets too, because the data size allowed us to calculate the sizes too. So we just take and put it like this. And the end buffer in user space that will be read from the channel will look like this. We have a small headline that basically tells us that in the current array we have this kind of events, so many events. Then this structure is event, it's just copied from the previous slides. It has some kind of items and it will be put forward depending on certain offsets. And serialization, well, I'm not sure if I need to describe it deeper. We just go through items, we copy it according to different offsets into user buffer, we copy the events, we set specific fields where we need to set them. Well, somewhere else, not on this slide, obviously. And then we send all this into user space. So why do we do this? I already partially covered this. We do not duplicate the data, there is no redundancy. We do not need additional synchronization of data between different objects and agents. So the algorithm becomes pretty simple. The serialization is not performed. Well, actually, what I will say, it says that we do not have multiple time. We do not perform serialization multiple times, but I mean, we do not have serialization for each of different agents. Obviously, it performs just when the events are read from the channel. And we also don't need to calculate the size of the buffer before the serialization, because we already know the size when we add those events. Okay. In general, just for a clear understanding how the whole flow of the event goes. Here, we get into the hook, the process is being carried out, ESF checks it, if they need to control or not. If it has to be controlled, we add this to the table, and then we will write them into channels. Okay, we write them. Yes, so here we start the writing into the channels. We check if they're filtered or not. If an event is filtered, we double check it. If this event was controlled or not. If it was controlled, we automatically decide based on what was said by the filter. If nothing was said, we drop it. If nothing is filtered, we add this to the queue here in the channels. And we double check it again. If it had to be controlled, we will wait. We will wait for the agent reply. If we don't have to do this, we just exit the hook, and that's all. This is the simple scheme for the whole presentation. So we now manage the kernel. Here we can sigh a brief breath of relief. It will be easier later on. Now, how do we work with this in user space? When it's about user space, I would say that we plan to use a library. I think it was shown on the first slide. I don't know if it's a good news or bad news. We don't have the library currently, but you can see how it should look like using this QR code. This is a link to the source code inside samples, inside a sample of an agent which I wrote. So how does the initialization happen? We take this, some collective structure about the agent. Basically, it's a descriptor file. We open our device, the charter device, which basically sticks outside to interact with the system. We register ourselves. This is a simple IOCTL. We check for errors. If there are no errors, then we are registered. Next, we have to set up the channels. It's the same collective structure about the filters. We can use stack. We can have multiple approaches here. It depends on your specialization and your skills. Here we use authentication channel because it's the more complete, let's say. We already know how to work with listen, we already know how to work with authentication channels. We open these authentication channels. Obviously, I will not go through error checks, you should know this. We subscribe to the type of channels for process execution. Now we subscribe, we double check it. Now something interesting starts. We create a filter as an initializing structure, which tells basically compare fields in using this logic, and we drop if they do not satisfy the conditions. And we say here that if a filter, or rather if an event has execution, and if path is target from bash, let me rephrase. If the process path is bash, and the target path is ping, which means is that bash is running ping, then it should be disallowed. And then we just add this to the channel. So this kind of filter uses authentication channel. It will disallow anything what's very similar to ping from bash. And I think there was a funny story connected to that. When I was debugging this, I basically prohibited the system to perform anything. Well, at least it got the signals. So after that, after we set up all the settings, now we can just run this. It's activated. It's a separate CTL which activates the Anon agent. I think there is no need for additional explanation here. And then channels start working. The channels work, we have events, now we have to read them. Since from the channel side we have polling implementation, I hope you don't need to be... Well, obviously, you should know what polling is. Basically, we have our threads with processes, and we try to wake up the kernel. And we basically say, please tell us when something happens here. Polling is polling everywhere. We just get to the channel, we wait for events, and once those events appear, we go into processing of these events. And before that, well, obviously we have to read them and then process them. When we read events, it's basically the same as lip-sync. It's implemented, well, basically like in Unix and POSIX. We can take and just read the channel like in VFS interface. We read the channel if the result is 0, because it cannot return read as 0, because we always read the add, which tells us how many events we have. We always have some number of events in this. Okay, so next we go into the array. for rich events. This kind of macros, if you worked with C++, basically is an iterator. You create an iterator, you initialize, and then you make it work. Since the head of the event looks like this is the size of an event and the signifier of the beginning of the structure. So we just take the initialization of data buffer. We know the size of the data since the event is specified in the header with items specified there, and we will just add using offsets and just go to the next event. I think it's a trivial, simple task. And finally, the control. Here you can see an example how to prohibit all Python scripts that use this framework. Once we get some kind of event, we check the flags, if this can be controllable. If it can be controlled, then we see, okay, so this is the process, and we check the interpreter. The interpreter is Python, and if it's Python, then we prohibit Python, because Python interpreter can be only if when the kernel, during reading the file with +x flag, was able to find plus user bin file. We did not prohibit all the scripts, but it's all about the filters. Did it turn out good? Well, yes. Now we have to know what do we do next. There are some short-term plans for development. And first of all, we need a wider pool of events, because of all the list of potential types, only 3 work. Those which I selected for debugging because I worked by my own, I didn't have enough time and I had a lot of work. Dynamic event format. There is something called protobuf, and I think this is the ideal solution for these kind of things, which allows us to specify the event format beforehand. It actually provides us back compatibility, changing schemes, but protobuf is really hard to get into the kernel. I think it's easier to create your own solution, maybe using additional buffers. We need to check their back compatibility. And what's interesting here, this kind of dynamic event format would allow us to work with external events. External events will allow us to create a different agent. It will not read, but will write events. So why do we do this? We need that. One of the requirements of the framework, which I put myself, is the consistency of events. If everything connected with the security will go through a single endpoint and will give you a result at a single endpoint, the life will get better. That's basically all the short-term plans, and maybe working with library. And we obviously we did not have improved the library, we actually had to create the library. As I mentioned, we don't have the library, and once we have the library, somebody's life will be better. And long-term, obviously, is off-stream, and the good news is that basically everything that's specified in the potential schedule in the pool of events is covered by LSM. And if it's inside the LSM, then the kernel containers don't really care if you created another workaround. It just works and lives there, it doesn't care about it. And finally is the problem with Linux subsystem audit, which sometimes basically stops the whole system even better than proprietary agents, even our agent. And that's all I wanted to say. These are the plans for the short to long-term horizon. And instead of conclusions, I decided that there are no conclusions. Everything I wanted to say I already did during the presentation. And now I think I would like to call upon the community to take part in this. This is upstream, ESF upstream. Unfortunately, I was not able to open the repository. I don't have enough rights. So we have GitHub Mirror for you just to go through the source code, maybe fork, maybe open some purge if you want. There's my Telegram channel. You can subscribe, and sometimes I publish some memes and some articles, and obviously publish oh,
Спасибо за внимание. Вот.
give me a mark. Maybe you can say that was a great presentation. And I would like to thank the Institute of Systematic Programming and Russian Academy of Science, helping me work with all these repositories and for communication between the interesting parties. So once again, thank you very much for your attention. I'm ready to answer your questions.
Спасибо большое, Тимур. Сейчас
Thank you, Timur.
вопросы из бота.
We will ask the question from our Telegram bot.
Хостовой системы
Do
и контейнеров.
event channels separation is supported in host system and using containers? I think this is a very good question, technically.
Если мне память не изменяет,
Unless I'm mistaken,
у LSM есть
LSM has hook-in C groups. Basically, the kernel does not care what's inside the container and what's outside the container. The only difference is that in C groups and namespaces, in the current configuration, as it is, we already have some information on the changed namespaces. So technically, I would delegate this channel of allowing containers or non-containers to the agent. The agents would do this. It's easier to do it from user space instead of trying to work from kernel if it's Docker, if container D, or any other container agent. I hope this kind of answer satisfies you. Thank you. Isn't creating complex filters in user mode is not something you would want to get away from with the decreased speed, and you would want to do something not. You would want to do this not from user mode, or there are some problems. Well, obviously, you would want to get away from complex filters in user mode, but the reality is that, at least I think so, about 90% of the cases are covered with the downloading of the correct globe inside the kernel. And I don't really understand how you can forego complex filters, which are basically business logic, not just technical tool in user space. So maybe you would want to forego this, but in my humble opinion, it's not possible. Thank you. Did you face code for checking the processing in terms of memory loss? We use bug-ons. Isn't this a question from Alexander Popov? No, we did not have this phasing. We debugged it. We have bug-ons and asserts all around. Still, everything is at the stage where even some basic features are not deployed. But obviously, it was not phased. I think this is the correct solution. We should do this, and it will be implemented in the future. Okay, thank you. Can we filter network connections individually for different ports? Yes, it is possible once we have network events. Once we have network events, we have events for network connections and network events. We don't have this now. Why should you go through these events in different channels, listen channel and authentication channel? Yes, I think I should give more explanation about the filters. Those filters are independent. They exist separately for each of the channels. They exist separately for each of the agents. They are not joined in any way. And this is more about flexibility of settings. But that's my answer. And the final question: can this framework be considered as an analog of EPP solution in an EPPF solution in an organization? Or maybe it means that there will be a security or protection of a service in an application. Okay, maybe I can read the question so that I can understand it. So EPP solutions. Maybe they mean endpoint protection. And what does it mean? It means some kind of service protection. Yes. If I understand the question correctly, I hope I will give you the correct answer. Originally, it was thought that EDR system would use it. If EPP is endpoint protection, then yes, the answer to the question is yes. This is exactly for this point.